Okay, so now we're going to do some kind of a word problem involving these things. So let's say you've got 3 roommates. And let's say that they're making a budget. They're going to make this budget in a kind of strange way. You would not normally do this, but let's do this anyway. So they're creating a budget. So Bob spends, let's say, 50% of his his outgoing money on rent. And let's say he wants to spend 30% of his money on food and 20% on entertainment. Okay, so that's one roommate. Okay, and let's say that Sophie spends 60% on rent, 25% on food, 20%, or sorry, that can't be right, 15% on entertainment. Okay, there's a lot of writing, a lot of numbers here. Amy spends, let's say, 45% on rent, 25% on food, and let's say 35% on entertainment. Okay, it's not enough. We still need more information from this. Yeah. It should equal 100%, yeah. Oh, which one? Oh, yeah, sorry, that middle one should have been 20%. Thanks. My bad. Okay, and then let's say they, in total, between the 3 of them, they pay $1,535 in rent, $745 on food, and $720 on entertainment. Okay. So the question is, how much does each person spend per month in total? Okay, it's kind of a mouthful. It's a lot of stuff to write down. I've used 3 chalkboards, so it's got to be a lot. Okay. So, I mean, we're asking how much does each person spend? So we've kind of got 3 unknowns, right? So there's, 3 variables. Let's say X is the amount that Bob spends. Y is the amount that Sophie spends. And let's say Z is the amount that Amy spends. Right, so these are the three things we're asked to solve for. Like, so that kind of, so if you're wondering, like, why did I choose these three variables, right? These are the three numbers that we want to find in the problem, right? How much does each person spend per month? Okay, so these are variables, but now we have to come up with some sort of equations. Any ideas what kind of an equation I could write down from this information? There's going to be three equations. Yeah. Yep. And then all the rest of them are going to be kind of similar. So just to kind of repeat that, we can take, yeah, so you know that they're going to pay this much in rent in total. So 50% of Bob's outgoing money is on rent, and then 60 and 45. So that gives us an equation that 50% of x plus 60%, so 0.6 times y plus 0.45 times z should equal 1535. Right? And then similarly, you've got 0.3x plus 0.25y plus 0.2z is 745. And then 0.2x plus 0.15y plus 0.35z is 720. Is it clear where I came up with these numbers? Okay, so this is a system of three equations with three variables. You could just, you could solve this using Gaussian or Gauss-Jordan elimination. That's one way you could do it. But since recently we've been talking about inverses, so I want to solve this using inverses of matrices. Okay, so, and we'll see some sort of benefits of that at the end of this example, but right, so I want to kind of think of this as a matrix equation, like A times X equals B, where A is a matrix, X is a matrix, and B is a matrix. And then I want to find the inverse of the matrix A. So this SLE, the system of linear equations, is equivalent to AX equals B, where A is the coefficient matrix, which just basically contains the coefficients of these equations. Okay, so all I've done here is I've gone through the three equations and written down all the coefficients. X is the matrix containing my variables, X, Y, and Z. and B is the matrix containing the right side of the equality, which is 15, 35, 745, and 720. Okay, so to solve this, to solve the system of linear equations, you know, basically is useful to compute A inverse, because then if I kind of multiply by A inverse on both sides, you can get that X is equal to A inverse B. Okay. Okay, so we're going to do a big kind of Gauss-Jordan elimination to find the inverse. Any questions at this point? Yeah. Yeah, so generally that's, okay, so one thing is this is a cap, so it's not the same X as this one, it's a capital X. And like, basically, so all we're trying to do is rewrite our system of linear equations in a different way using matrices. And what I claim is that, yeah, if X is equal to the three variables like this, A is like this and B is like this, if you kind of wrote down what this equation means in matrices, if you did the matrix multiplication, like it'll tell you, basically you'll take this top row times this column, that'll give 0.5 times X, 0.6 times Y, 0.45 times Z equals 135. And that'll give me my first equation. So like basically this is just a way of rewriting the same thing as before. So you want this capital X to contain your three variables, basically. But yeah. Any other questions? Okay. So we've got a big row reduction to do, big Gauss-Jordan elimination. So I start by rewriting my matrix. Okay, and then I write the identity matrix on the other side. Okay. One thing I don't really like is decimals. I don't know how you feel about decimals, but I'd rather have integers. So what I'm going to do is just kind of clean this up first. I'm going to take my first. Well, I'm going to do two things at once. Remember, when we're doing Gauss-Jordan, we really want to get a 1 here. So I'm going to get a 1 here by multiplying this row by 2, right? 0.5 times 2 will give me 1. So I'm going to take 2 times row 1. So that's going to, okay, it doesn't solve the decimals, it doesn't make these integers, but it gets me my 1 where I want it, right? That's one good thing. And then at the same time, I'm going to kind of make these rows look a bit better. I'm going to multiply them by 20. You don't have to do this. It's not required, but you'll see that it makes the numbers a bit nicer. So here I get 1, 1.2, and 0.9, 2, 0, 0. Apologies, I'm kind of writing smaller than usual because these are big matrices. 6, 5, 4, 0, 20, 0, and then 4, 3, 7, 0, 0, 20. So I'm just multiplying rows by constants. That's an allowed thing that you can do, right? You're allowed to multiply rows by constants. And like I said, you don't have to do this. If you just dealt with the decimals, that's totally acceptable. You don't have to do this, but it just makes it a bit nicer for me anyway. Okay, so I've got my 1 in the correct position, and now I want to use it to get zeros on the other rows in that column. So I'll take row 2 minus 6 row 1, and row 3 minus 4 row 1, which doesn't change my first row, right? When you write these things, right, this always, so the first row that you write is the one that's changing. So we're saying we're changing row 2 by subtracting row 6 times row 1. So this doesn't change the first row, right? We're changing row 3 by subtracting 4 row 1. Okay, so these ones I know I'm going to have zeros because I set it up that way to get zeros, right? That's why I subtracted 6 of the 6 and 4 times row 1. Here I'm going to, okay, now I'm back to decimals again. So it's negative 2.2. Negative 1.4, negative 1.8, and 3.4. Then on this side, I've got 2, 0, 0, negative 12, 20, 0, negative 8, 0, 20. Okay. I'm now looking at that value, right? And I want to get that to be a 1. So it's not hard to make a 1, right? I just, as long as this is not a 0, which it's not, I can just divide this row by this number. So I take, it's kind of a weird thing to do because it's a negative number and it's a decimal, but there's nothing wrong with this. I'm going to take row 2 and divide it by negative 2.2. I think at this point I started, if you start doing this, you'll realize that you're now going to have infinite decimal expansions. So now it might be a good idea to change to fractions instead of decimals. So I'm going to write this 1.2 as 6 over 5, which is the same thing, right? If you compute 6 over 5, you get 1.2. This one I'll write as 9 over 10. So let's just do fractions from now on. And the reason for that is coming up here. Here, the correct value is 7 over 11, which if you try to write the decimal, it goes on forever, so you can't really write it down. So you should probably write 7 over 11. And here I get another infinite decimal, 60 over 11, negative 100 over 11, 0. The last row is 0, negative 9. Oh, I guess I decided to get rid of the fractions again. So let's multiply the third row by 5. Okay, so that's where I'm getting these numbers here. Any questions about this step here? I thought I should at some point give you a complicated example of Gauss-Jordan elimination. So now we're doing a complicated one. Okay, so now I've got my 1. I want to get rid of this 6 over 5, and I want to get rid of this -9. I take row 1 minus 6 over 5, row 2, and then row 3 plus 9, row 2. Right? And if before this, if the system for like the systematic approach wasn't clear, like hopefully it's getting clearer and clearer that all you do is you just divide a row to get the right number. You then use that to get a 1. You then use that 1 to kill everything else. Repeat, repeat, repeat all the way, you know. So, okay. So here we're going to get 1, 0. I mean, we know it's going to be here, right? We set it up that way. And then the only questions are like, what are these values? So here I get 3 over 22. You can probably take my word for that. 7 over 11 here. And 250 over 11. And here I get negative 50 over 11. 120 over 11. 0. 60 over 11, lots of over 11s in this. Negative 100 over 11, 0. 100 over 11, negative 900 over 11, and then 100. So for example, if you're wondering where these numbers came from, for example, like where did this come from? This was, I took my value on row 1, which was 9 over 10. And then I subtract 6 over 5 times the value in row 2. And then hopefully you get 3 over 22. So that, you know, that explains, for example, where this comes from, right? And everything else is kind of the same. Okay. Okay, so now I want to get a 1 here. So I take 11 over 250 times row 3. So everything stays the same except for the third row. Okay, this one becomes 2 over 5. This one becomes negative 18 over 5. This becomes 22 over 5. Is that right? No. Maybe it is. Yeah, that seems right. Okay, I know this was painful, but we only have one more step here. Row 1 minus, what is it going to be? 3 over 22, row 3, right? And row 2 minus 7 over 11, row 3. Right, again, I'm just trying to annihilate these two numbers. So now I know exactly what I've got here, right? Okay. And then again, you can probably take my word for it. This is negative 23 over 5, 57 over 5, negative 3 over 5, 26 over 5, negative 34 over 5, negative 14 over 5, 2 over 5, negative 18 over 5, and then 22 over 5. A lot of over 5s. Yeah, so this is a long example, but yeah. So these three, 26 over 5, negative 34 over 5, and negative 14 over 5. Yeah, sorry, everything is getting a little squished. Okay, but now we are pretty, well, we're almost done. This is the inverse of that matrix. So this, we have to kind of go back and try to remember what we were doing at the beginning, right? But this matrix on the right side is the inverse of A. And now, all we have to do is one little matrix multiplication, and then we're done. So, right? Because at the end, we get x is equal to A inverse times B. All we have to do now is multiply A inverse times B, and then we win. As long as we've done all the calculations correctly. Okay, so now we want to take this matrix, negative 23 over 5, 57 over 5, negative 3 over 5, 26 over 5, negative 34 over 5, negative 14 over 5, 2 over 5, negative 18 over 5, and 22 over 5. This inverse matrix, we want to multiply that by B, which we define to be these three numbers like this. Okay. So I'll just kind of write down how you would do the first row, right? So, or the first entry in this multiplication, I would take this times this. Plus 57 over 5 times the other thing, right? 745. So then kind of minus because it's a minus. So minus 3 over 5 times 720. Okay, and then you do 3 more of these calculations. At the end of the day, what you get is 1,900 and 1,100. Okay. So my final answer is x equals 1,000, y equals 900, and z equals 1,100. Okay. And hopefully if you plug those values back into the original equation, the three original equations, you would actually get, for the first equation, you get that it equals 1535. The second one equals this, and the third, you would get that all the equations are satisfied. So this is how much Bob pays per month. This is how much Sophie pays per month. This is how much Amy pays per month in total. Okay. Any questions about this? Okay. So that was a lot of work to get this inverse matrix. Okay? I mean, if you were doing this, you would not want to repeat all of this work, right? That would really suck. So here's one nice thing about this approach is, let's say that in this situation with these 3 roommates, let's say that the landlord increases the rent from $1,535 to $1,550, okay? So the rent has now changed. And let's suppose that these 3 roommates want to keep the same percentages. So they want to keep Bob pays 50% of his outgoing money on rent and 30% on food, 20% on entertainment. But now the total rent has changed. One good thing is you don't have to do all of this again to compute the numbers. All you have to do is this step, right? I've already got the inverse of A. A hasn't changed. If we're keeping the same percentages per month for each person, A has not changed. So the inverse is the same. You don't have to repeat all of that work. If you just change this number, you just change that number and repeat the matrix multiplication, which is a lot easier, right? Whereas if I did this with Gauss-Jordan elimination, when you change the number, you might have to then go through the whole row reduction again, the whole Gauss-Jordan elimination again, and that would be a pain. Okay. Is it clear what I'm trying to say here? That this is nice because I've got my matrix, my inverse. If one of these changes, you just repeat the multiplication. You don't repeat the whole process. However, if the percentages from the beginning change, then you're screwed. So if Bob says he's going to pay 45% in rent or something, then you have to start over. Okay, any questions about that? Okay, so let's, for the last kind of 20 minutes here, let's start on another topic. So we're now moving to chapter 3. Which is linear programming. We're going to start with something which is hopefully familiar from high school. So we're going to start with linear inequalities. Okay, so for example, if I wrote down, and note that, so I'm talking about inequalities. So it's a little bit different than linear equations, right? So previously, in chapter 2, we were talking about solving systems of linear equations. Equations means, like if something's an equation means it has an equal sign in it, right? But here we're talking about inequalities. So inequalities will have like less than or, things like this or this. It's not an equal sign, it's an inequality, right? So for example, if I write down 2x plus 3y is at most 12. Okay. So you might want to, so one way to kind of analyze this is to graph the solutions to this inequality. Okay. By the way, right, this means less than or equal to, right? Not greater than or equal to. So yeah, so you probably have seen something like this in high school, right? So, okay, first of all, what I'm going to do is I'm going to graph the line. So if I take 2x plus 3y equals 12, that'll form a line, right? You could solve for y and get that in. You could get the slope in the y-intercept or whatever, right? I think actually an easier way to draw this. So I want to draw just the line 2x plus 3y equals 12. If I think about it, if I set x equals 0, then I'll get y is equal to 4, right? So when x is 0, y is 4. And when y is 0, x is 6, right? So to graph this line, I can just take these two values and just run a line through them. So this came from when x is 0, y is 4, right? So the height is y, right? And when y is 0, x is 6, right? So this is the line where 2x plus 3y equals 12. Okay. So you might remember these kinds of things from high school, that if I want to graph the solutions to this inequality, what I want to do is shade one side of this line, right? Can anyone tell me a good way of figuring out which side I should shade? Do people remember how to do this? I feel like I did this maybe in grade 10 or 11 or something, or I don't know. No, you don't remember this at all? Who remembers this kind of thing? No? Yeah? Huh. Huh. Interesting. Okay. Yeah, things have changed in the last however many years since I've been in high school. Well, okay. Here's the trick to figure out which side is the solutions to this. So I've got this line here, right? That's the line 2x plus 3y equals 12. On one, like, I want to know, basically I want to know, are the solutions to this inequality, are they from this line upwards or from this line downwards? It's going to be one or the other. And if I kind of think about, on one side of this line, I've got the origin, which is a really simple thing, x equals 0, y equals 0. What you can do is just plug in x equals 0 and y equals 0, and then ask yourself, is the inequality true in that case? So plug in x equals 0, y equals 0. And then we get 0 is less than or equal to 12, right? That's what you'll get here. And remember, well, I don't know, the alligator eats the big side, right? So this is true. Okay, so that means here the inequality is satisfied. So the solutions are everything below this line. Or I should say on the line or below the line. So the solutions to the inequality are the shaded, the elements of the shaded region. So in other words, basically all you have to do, you graph your line, you check a point that's below the line or above the line, and if that point satisfies the inequality, then you need to shade towards that point. So for example, if this was the other way around, if this inequality was the other way, I would shade above the line, because 0, 0 would not satisfy the inequality. So this is not like if the inequality went the other way, this would not be a solution, so I would shade above the line. Now in principle, you don't have to try x equals 0, y equals 0. You can plug in any values you want, but I think hopefully it's clear that like that's the simplest thing most of the time, right? You plug in zeros, you just get zeros, right? Okay. Any questions about this, like what this means, or yeah? Yeah, if it was strictly less than, then what I would do is maybe draw a dotted line on this line, which would mean that, yeah, this line is not included, but everything below it is. we're never going to, in this course, we're never going to see anything like that. But yeah, if you wanted to say strictly less than, you could say, you could put a dotted line and say, it's everything below this line, not including that line. Okay, any other questions about that? Okay, so we're not just going to be interested in single linear inequalities. We're going to be interested in systems of linear inequalities. So a system of linear inequalities well, it's pretty much the same thing as we were doing before, right? We were doing systems of linear equalities. Now we just have inequalities. So it's like you have a system of kind of like things that look like equations, but all the equal signs will look like this instead of equal signs, right? This way or the other way. So it's a set of linear inequalities and if I have a system of linear inequalities, the set of points that satisfy all of the inequalities is called, well, it has a few different names. So sometimes it's called the feasible region or set, or the solution region, or sometimes set. And it's usually written as S. So that's your notation. Kind of unfortunate that, like, in probability, S was the sample space, and now here S is the solution space, but yeah. This is a different S than before. So let's do an example of how to graph these feasible regions. So graph the feasible region of, let's say, 3x plus 5y is at least 30, 4x plus y at least 20, x at least 0, y at least 0. So in other words, we want to graph this, and we want to shade in all the areas where all four of these are satisfied. Okay. So as a first step, always in these things, like we did last time, as a first step, just start drawing your lines, you know? Just start drawing the correct lines. So if I wanted to draw this line, if I put x equals 0, then that means y would be 6. So let's say 6 is around here. These don't have to be perfectly to scale, right? When y is 0, x is 10. And your lines don't have to be perfectly straight either, obviously. When x is 0, y would be 20. 20, I don't know where it is. It's up here, let's say. And when y is 0, x is 5. Okay. And then this line is kind of, this is just the vertical, this is just the axis here, the y-axis. And this one is just talking about the z-axis. Okay. And now for each of these lines, we need to determine which side to shade. Okay, so for the first line, which is this one, so this is the line, the solutions to 3x plus 5y equals 30. That's this line here. So for this line, should I be shading above the line or below the line? So for this one. So I guess this inequality, which is this line here, should I be shading up or down? Yeah. How come? Yeah, exactly. We can just plug in the origin into this. So 0, 0, at least 30 is false. So therefore, you want to shade above the line. So for this one, I'm just going to kind of put arrows here, saying we're shading above the line. I'm not going to shade it yet, though, because I don't really know, because we have to satisfy all the inequalities, so you have to be a bit careful. For this one, I'm also going to shade above the line because the 0 is not bigger than 20. So I shade this way. For x at least 0, that's this line, and I'm shading, everything with the x bigger than 0. And here I'm shading above. So if we ask ourselves, what's the feasible region? It's all the points that satisfy all of these inequalities. So if you think about it, so for example here, this would not be feasible because it doesn't satisfy this inequality. It's on the wrong side of this line. So you want to pick all the points that are on the correct side of every line of your, so it would be everything over here. So everything on that side of this kind of boundary.